Hi, this is Kevin Trainer, and I'd like to welcome you to my lecture on Chapter 14 from the Murach MySQL book, second edition. And Chapter 14 is entitled How to Use Transactions and Locking. And this is one of the final chapters that we're covering in this particular rendition of the course. And these are um, these are kind of maybe fancy developer uh, related issues, but if you don't understand them, um, you can get into trouble no matter what level of use you're making of a database. So we're going to go through this. This isn't these aren't skills that you need to put into action for your course project, for instance. But this is stuff that's good to have on your mind for later when you're doing this in your day job. Okay? So the objectives for the chapter, I'm going to leave you to read on your own. And the first thing that we're going to see here is some code that we haven't learned about yet. And this is because it's very developer oriented. There are these things called stored procedures. And they're kind of like scripts, okay? They are a combination of SQL scripts with programming language, the constructs wrapped around them. And they allow us to write scripts that are kind of smarter, okay? And scripts that can kind of run unattended in a lot of ways. So here, I just want to show you that they've created a procedure. And again, there's a whole chapter on how to create a procedure that we haven't covered. And we declare some variables and we start a transaction. That's going to be very important to us. So there is an SQL statement start transaction. And then we do an insert into invoices. And then we do an insert in invoice line items. And then we do another insert in invoice line items. Okay. And then we've come to the end of our unit of work. Okay. And so what we want to do is if all of those statements had executed successfully, which is what we test when we say if SQL error equal false, then we're going to issue two SQL statements. Commit, which is going to be really important to us, which commits our changes to the database, and then a select that puts out a message. Okay. Else, if there was an SQL error, then we're going to do the opposite of committing. We're going to roll back, and that's pretty important to us too. And then we print a message there as well. And those are wrapped with this if, else, and if. Okay? So what does it mean to start a transaction, and what does it mean to commit, and what does it mean to roll back? Okay. Well, let's talk about that. So what we want to do when we're working with our database is we always want to leave the database in what we call a consistent state. Okay. And that's pretty easy to do in a world where the work that we're doing can always be can always be implemented with a single SQL statement. Because we issue the statement, we send it to the server either in an SQL script or one of those stored procedures that we see back here on slide 3. And if it's only one statement long, then it either runs or it doesn't run. Okay? It doesn't half run. Okay? That's great. Okay? What if we have a unit of work that's more complex than that? We have in the code that we see here on slides 3 and 4, we have exactly that. Because what we want to do is we want to put a new invoice in, okay? And it consists of one row inserted into invoices and 2 rows inserted into invoice line items. And it's only if all 3 of those have worked successfully that we are willing to commit that change, because that's a transaction. That's a full unit of work in terms of our application. So we want those to either succeed or fail as a whole. So the transactions allow us to surround a series of SQL statements with a start transaction and a commit, such that we will only get a commit if we didn't get any errors in the statements that we bundled inside the transaction. So when we come to the end, we've got 2 possibilities. We've got a commit, in which case it actually changes the data on the database, okay? And it writes the changes out to the binary log file, okay? Or if something has gone wrong, it rolls them back. So if some of the changes were made but not all of them, it rolls the ones that were made back, and so we get to the state that we were in before the transaction. So transactions allow us to have units of work that take more than one SQL statement and still be assured that we're always going to leave the database in a state that only has a whole unit of work or not that whole unit of work. We can't get it into some half-done state. So that's our goal, right? So when would we want to use it? When you code 2 or more insert, update, or delete statements that affect related data. Okay, so it's not just any 2 or more SQL statements. They have to change the state of the database. So what are the SQL statements that change the state of the database? Well, they're insert, update, and delete. When you move rows from one table to another table by using insert and delete statements, okay? So we're going to insert it into one table, delete it in the other table, okay? So that's really 2 or more statements. Whenever the failure of an insert, update, or delete statement would violate data integrity. Okay? So, again, we want to do our inserts, updates, and deletes in a series that takes into consideration things like referential integrity, okay? And it's only if everything goes as expected that we're going to commit the changes. Now, it's possible to have save points, which is to say we can save parts of our work along the way throughout the transaction. Well, why would you want to do that? Well, you might do that if you have a transaction that has a lot of work in it. Okay? So here we see that save points, as we have described here on slide 6, they are a sub-item under transactions. So you can't have a save point until you've started a transaction. And here we have, we start the transaction, we say save point before invoice, insert into invoices, blah, 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 save point before line item 1, then we have save point before line item 2, insert, and one more insert, then we roll it back to the save point called before line item 2, then we roll it back to the save point before line item 1, then we roll it back to the save point before invoice, then we commit. Well, is this a real use case? No, probably not, but we can save intermediate points within the transaction if that's going to be helpful for us. Okay? Now, so one of the problems that can go wrong when we're doing these inserts, updates, and deletes is that parts of a transaction can fail. Another problem that can go wrong is as soon as you get into a multi-user application and you've got more than one user using your application, they can be trying to update the same records and they can begin to interfere with each other. So for instance, here we have on slide 8 two transactions that retrieve and then modify the data in the same row. So we say start transaction, update invoices set credit total equals credit total plus 100, where invoice ID equals 6. And it says the select statement in transaction B won't show the updated data. The update statement in transaction B will wait for the transaction A to finish. And then we commit. The select statement in transaction B will display the updated data. The update in transaction B will execute immediately. So let's find transaction B. So in transaction B, we're doing the same stuff. So we select invoice ID credit total from invoices where invoice ID equals 6. Okay, so that is either going to wait for transaction A to finish or not. Okay, if it waits for transaction A to finish, then you're going to get, it's going to be executed based upon the new values. Okay, if it doesn't wait for transaction A to finish, it's going to give you an answer based upon the old values. Okay, and then of course the update, if these two transactions were not coordinated at all, it's possible for one of them to lose their work. Where you do the it's called the race problem. We both go to update row 6, and so we both get the prior value. You return your new value first. I return my new value over top of yours, and I wipe out your work. Okay? So how do you test these kinds of transactions? Well, you open a separate connection for each of the transactions. You can do that in Workbench. And you execute one statement at a time, alternating between the two transactions. So you could do this as a demonstration. All right. Now, we're not always going to get the behavior that we want. So sometimes what we want to do is we want to We want to provide locking in the database such that we're getting the right combination of performance, like how long it takes to do a select, an insert, an update, or a delete, compared to how reliable the data is. Okay? And the performance and the reliability are kind of inversely related to each other. Okay? So if you want to get the quick answers, then if you want to get the quickest possible answers, then you you adjust the software such that you claim, well, I can tolerate some inaccuracies. If, on the other hand, you want to squeeze out all potential inaccuracies, then you're going to slow down the response time of the database. So let's talk about the different levels you can set this to. First of all, let's talk about the kind of problems that can happen. Lost updates, I mentioned that scenario already, dirty reads, non-repeatable reads, and phantom reads. Let's talk about what those are, because there's not a slide on each of those. I thought that there might have been, but there's not. Lost updates. Okay. So my program and your program are both attempting to update row 6. We retrieve row 6. We get the current value. You send your update. I send my update. It overwrites your update. Your update doesn't get considered at all. Yours is a lost update. Dirty reads. A dirty read is a read from it's a read from state of the database that is inconsistent. So some of the data, let's say you're executing a transaction, I do a select, okay? So I do a read while your transaction is executing. I get some of your changes in my answers. Non-repeatable reads and phantom reads are kind of similar things. The question is, are we going to wait to make sure that we're committed to all the changes before I go and get to read my data? Okay? If we're not, maybe I can be reading the data while you're changing yours, or maybe I can read changes that you have not committed. Maybe I can read old data while you're committing new changes. There's all kinds of ways to get out of sync. So how do we stop those things? Well, we set the product to be as careful as we're willing to pay for in terms of execution speed. Okay? So there is an isolation level that you can set per transaction. You can also set it for a session. And the least isolation that you can get is read uncommitted. Okay, so that doesn't present any problems. That will allow my select to read your updates even if you haven't committed to them yet. Read committed can read your updates only after you've committed them. Repeatable read will solve dirty reads, lost updates, unrepeatable reads, and the setting serializable will solve all of them. Now, how do you decide on this? Well, it really depends, okay? Oddly enough, there are quite a few applications where there are not more than one person updating the same data, okay? Or more than one person updating the same data doesn't have a lot of bad side effects. For instance, let's take let's take some kind of personal account that we have. Let's take our LinkedIn account, okay? So I log on to LinkedIn and I change part of my profile and then I log out, okay? Well, what happens if somebody else logged in at the same time? Well, that's okay. If somebody else is going to log in as me, they're going to change stuff. If I log in over top of myself and I get things confused, well, it's not the end of the world, okay? Other people should not be logging in. In a lot of workplaces, people, the number of people are going to work with one customer at a time is limited. Maybe only one employee has one group of customers at one time. One employee for shift deals with customers in the eastern region. Another employee deals with customers in the Midwest, another in the West. And the fact is that they're not actually working on the same data. There's all kinds of schemes like that. But as soon as you get down to situations where more than one user could be updating the same data, like here's a classic instance. Let's say we have an e-commerce application where we're selling t-shirts, okay? And there's lots of customers who are trying to buy t-shirts online. And we're trying to keep track of how many of a given size we have at one time. Well, if we don't pay enough attention, we're going to tell somebody eventually that they've bought a t-shirt that we don't have for them. And we're going to get things out of sync. If we have the problem with, if we go back to lost updates, if you've sold a t-shirt and I've sold a t-shirt and we both go back and we do the update, and if we update it over top of each other, we're going to be left thinking we've got one more t-shirt in inventory than we actually do. So sooner or later, our inventory is going to be really out of whack. So it really depends on how likely these things are to occur. And these are the kinds of decisions that you would probably, as a developer and a designer, you would talk over with the DBA group. Now again, when do you have to worry about these things yourself? Well, if you're like me, if you're a sole practitioner, and you are implementing your system at your local ISP, okay, well, you're going to get whatever default settings MySQL might come with, and maybe that doesn't completely serve your needs. In that case, you're going to want to come back to this and give it a look-see. So in terms of picking an isolation level, the serializable is the safest and the slowest. Read uncommitted is the unsafest and the fastest. And it's it gets slower and slower as you go down the page. So you just need to trade it off. It could also be true that if you have a a pretty small e-commerce application, serializable wouldn't be too much of a performance penalty at all. You just don't have that many people pushing the server, in which case turning on that setting um, doesn't really compromise anything. Okay, so what's the syntax that you use to set this stuff up? Well, you can say the set, and you can either do it globally or for a session or for a transaction. So if you set it globally, that sets it for the server. Set it for the session, that's for the length of your connection. Or you can set it for the transaction, and then you say isolation level, and then you pick one of the levels. Okay, so here's one that sets it to serializable for the next transaction. Set, transaction, isolation, level, serializable. Set the level to read uncommitted for the current session. Set session, transaction, isolation, level, read uncommitted. Okay. Set the level to read committed for all sessions. Set global, transaction, isolation, level, read committed. So again, we're trading off speed for safety. We have one further problem, and it's called deadlocking. Okay, and this is a thing that can happen when we begin to introduce transaction isolation levels. When we set it to its highest level, which is serializable, then one transaction is going to wait for the other transaction to finish. Okay? So for instance, if we have a transaction A and transaction B, we're going to start transaction A, and we're going to wait on transaction B. So the question is, who gets these things one at a time? Okay, I'm going to back up and contradict what I just said. So within a transaction, so if you look at transaction A, first we're going to do an update to savings, then to checking. Within transaction B, then we're going to do an update to checking and then to savings. Okay? So what can happen is if we're doing things in conflicting orders, we can get to the point that we're halfway through transaction A and halfway through transaction B, and transaction A can't do its last half until transaction B does its first half, and they're waiting on each other, and we call that being deadlocked. A really easy way to prevent deadlocks is to always use the table in the same order. So for instance, use do checking, then do savings. So what we're saying here is, instead of having the version of transaction B that's in the middle of the page, have the one that's at the bottom of the page that does it in the same order as the one at the top. And just because of the logic and how things follow each other, they can't deadlock. It's the combination in the middle that gets you to a possible deadlock. How to prevent deadlocks? One, don't allow transactions to remain open for very long. Okay, so make them pretty atomic, pretty short. Two, don't use a transaction isolation level higher than necessary for the job that you're doing. Okay? Three, make large changes in the database when you can be assured of nearly exclusive access. In a lot of places, that's overnight, over the weekend, over a holiday. Uh, and the other one is consider locking when coding your transactions. Locking will keep other people from using the table until you're done. Okay. So, how do you decide how to act on this stuff within the chapter? We've come to the end of the chapter. Well, for this course and for the project that you're doing, you don't really need to act on any of these things. Okay. Um, we're putting together a very simple single user application, um, and we're not doing things that we don't have the problem that we need to worry about transactions. Okay. In the real world, if you have an application that does more than one insert, update, or delete that need to be coordinated to become a unit of work, then you have to start to implement transactions. And then you get all the kind of implications that we talked about. Would this be work that you'd have to do yourself? In big shops, usually not. In big shops, you might have to do some of the implementation yourself, but the strategizing would be done with people from the DBA group. If you're a sole practitioner, like me, well, then you're going to have to deal with some of these issues on your own. And if you want to be really safe, then use very conservative settings. And if you're getting the response time that you need, then you're fine and safe. If you use very conservative settings and you're not getting the response time that you need, well, then you need to back it off until you get the response time that you need. So this is just the beginning of some of the complex database issues that you need to think about when you deploy an application into production. And if you have a lot of support and you work in a big shop, there'll be more than enough people to tell you what to do and that you can't do exactly what you want. And again, if you're working on your own, well, it's going to be different. So with that, I'm going to say bye until next time. Bye-bye.